So this is part one of a video series concerning the standards involved in fourth grade geometry. So we're going to look at several tasks that will either isolate one standard, or we will look at a task that will involve multiple standards like the one we see here, where we've got three different fourth grade standards involved. So this first task, really the purpose of it is just to gain experience drawing and measuring angles. Students trying to develop and understand this additive structure, how we can add angles together and subtract angles as well. And it gives the students a good opportunity to work with mathematical practices number 5, where they use appropriate tools strategically. And we'll look at a protractor and how we can use that protractor to construct angles. Now remember, it's not an exact instrument, but it does allow the students to derive an angle that is pretty good approximate to that angle. So what we have here on part A, it says draw an angle that measures 60 degrees like the one shown. Okay, so when I go to my protractor, I'm looking at each of these tick marks. So this would be 0, this would be 10, 20, and we see the 90 degrees. So if I want one that's 60 degrees, I'm going to start and draw this initial segment, and then go ahead and measure the 60. So there is another angle that measures 60 that's like the one above, and we'll call it A, B, and C, just kind of duplicating it and reproducing the angle. Part B says draw another angle that measures 25 degrees. It should have the same vertex and share the same side as BA. Well, we know that this is, here's our 90, and we said this was 80, 70, here's our 60 degree. Now, it wants us to draw another angle that measures 25 degrees. So we've got 10, 20, and then this segment right here would be 25. So I'm just going to draw my line there and label that this is 25 degrees. We know that this entire angle here is 60. Just don't know what this is now. And it should have the same vertex. So it does, shares the same vertex as B, and it shares the same initial side as BA, or ray BA. How many angles are in the figure that you just drew? So we look at that, we now see that we've got 1, 2 angles, and that's question, part C is asking how many angles did we draw? So part D just says make a copy of your 60 degree angle, draw a different angle that measures 25 degrees and has the same vertex. Well, I just want to look at now a different angle measure, or 25 degrees, than I did earlier. But if I go back here, how many angles are in there? Let me come back to part C. What I know is I've got this we'll call this C. So we've got C, B, A. and we'll call this one D. So I've got CBA, angle CBA, and I know that that's going to equal 60. And I also have angle CBD, which I don't know, angle CBD, which I don't know. And then I have angle DBA, which is 25. Okay, so a way to figure that out is you can create an equation, and I can subtract 25 from 60, or I can add up from 25. So if I have 25 and I add 5, I get to 30. And if I add 30, I get to 60. So what did I add? Well, I added 30 and 5. So what does that mean? Well, that means that x is equal to 35. Or I could have subtracted 60 from 25, or change that to 59 and 24 and still get 35. So I'm going to get 35 degrees. And then jump into D, it says make a copy, draw a different angle that measures 25. Well, what that would involve is my initial side, my 60-degree angle, and then creating one that is 25 degrees, which is, I would have to adjust my protractor. So you're looking at something like that. It's that additive measure. So now that gives me a new angle. So this would be C, B, and A. So angle CBA is equal to 60. And then we'll just add a point here. And we'll have angle ABE, and that's equal to 25. So when we sum those together, we would get a sum of 85 degrees. So I'm still sharing this segment BA, still being shared. I've just created a new angle, and that new angle is angle CBE, which is just the sum of 60 and 25, which would be the 85 degrees. So let's look at task number 2. Notice it really just focuses on the standard 4.G.1. So we're looking at drawing points, lines, line segments, rays, and angles, looking at perpendicular and parallel lines. So we're going to look at our alphabet and answer some questions based on this standard. So how many line segments are needed to make A? So when we're thinking about the letter A, how many line segments are needed? Think about what's parallel, what's perpendicular, that mindset. Now the letter A, I'm just going to draw it again. Let me use my segments here. So when we look at letter A, it's composed of 3 line segments. So we can see the 1, 2, 3 line segments. They meet in 3 different places. They actually form 5 different angles. They form an angle here, 1, 2, 3, 4, 5 different angles. And 3 of these angles are acute and 2 are obtuse. So students will be able to count angles and see that angles are greater than 180 degrees. And so that's important for students to be able to identify that so they can see what angles are larger than 180, larger than 90, smaller than 90. Students might see the letter A as being composed of 5 line segments and 2 straight angles on the sides of the letter A. That may be something that the students see. But none of the line segments are parallel and none of the line segments are perpendicular when you're looking at the letter A. Part B. So we can build all these letters from line segments and arcs. So I want you to build all the capital letters with the smallest number of pieces and where each of the pieces are line segments. So the hardest part, really, the hard ones are the ones with the curves. And if you look at the letter B, we see that we've got, kind of looks like E, but we have the curves, okay? So B can be made from 1, 2, 3, 4 line segments and then two semicircles. And then you can see that we do have some parallel lines here. We have parallel lines here and here. All those would be parallel. And then we also have some perpendicular. So we would see that these 3 line segments are all perpendicular to this vertical line segment, and we can notate that. We can notate that with the little box in the corner. So part C says which letters have perpendicular line segments. So when we get to part C, we're thinking perpendicular line segments. We want the students to start to identify that, and we'd see, yes, B does have that, and D has the perpendicular line segments, and you can see that in E, you see that in F, you see that in H, you see that in L, parts of P, parts of R, and then T. And those would be the ones that have perpendicular, so they have this look where they meet at this 90-degree angle. Part D says which letters have parallel line segments. So when we're drawing that, we're thinking lines that never cross. Now, which of the letters have parallel line segments? Well, we can see that B has parallel line segments. D, E, and F, H, M has parallel line segments, as well as N, as well as R. U have on the letter U, it has some segments that are parallel, and then also Z. So some of these letters, think about some of the letters that have parallel and perpendicular. So if you're thinking which ones are parallel and perpendicular, that would be letter B, D, E, H, and R. So those would be the ones that contain both of them. So that is a task that allows the students to hone in on look at the lines, the line segments, the angles, perpendicular and parallel lines, and being able to identify those on 2-dimensional figures. That is part of 4.G.A.1. Looking at task 3, where we're looking at different quadrilaterals, looking at examples and non-examples. So this hits 4.G.2, and that standard talks about classifying two-dimensional figures based on the absence of parallel or perpendicular lines or the presence of angles of certain sizes and being able to identify certain specifics. So here we're talking about quadrilaterals. I want to see examples and non-examples. And again, this task builds on geometric knowledge that students have developed way back in second grade, actually. You can look it up. It's 2.G.1. And so in this task number 3, students are basically using the definitions that they were learning back in second grade that are given for different types of quadrilaterals and what they know about parallel sides, and being able to identify how a square fits all the definitions and be able to explain why. And by drawing examples and non-examples for each kind of shape, students get to explore these different properties and how they relate to their prior knowledge and the attributes of a square. So let's start with the parallelogram. Be able to draw examples and non-examples. So with the parallelogram, remember what we're looking for. It's a quadrilateral with what? With 2 sets of parallel sides. So we're going to look at an example. And a non-example. So I'm going to use my line tool, and so the idea was to create parallel sides here and parallel sides here. So that would be an example, 2 sets of parallel sides, and then I can draw a different version of that if I want. I can draw a square. See the parallel sides here, and my parallel sides there as well. A non-example. Well, I need 2 pairs of parallel sides. Well, a triangle defeats that. For one, it's not a quadrilateral. I can also look at a trapezoid. Trapezoid is a quadrilateral, and it does have a pair of parallel sides, but not 2 sets of parallel sides. It just has 1 set. And then I could look at one where I have maybe a little bit of a tilted line here, a little bit here. Where it shows that this line and this line would not be parallel, and this one would not be parallel. Even though it is a quadrilateral, that would be an example of not having one. And then if I let's take like one of the letters that we looked at earlier. Let's take that L shape. I do have some parallel lines. I have more than 2 sets of parallel lines. And I also have 1, 2, 3, 4, 5, 6 sides. So that kind of takes you out of the whole idea of thinking that it's a parallelogram, because a parallelogram is a quadrilateral. So let's look at an example of a rectangle. And a rectangle is going to be a parallelogram. So we've already got an idea of what that looks like. Parallelogram with what? With 4 right angles. So let's look at an example. Non-example. This would be an example of 4 right angles. Notice it's also a parallelogram because it has 2 sets of parallel sides. We could look at a tilted square, also known as a rhombus. We say diamond, but rhombus is really your the correct term for talking about that. But here you got 4 sides, you got 2 pairs of parallel sides, and you've got 4 right angles, which is also a square. Some non-examples would be, well, it is a parallelogram, but in this case, notice the angle measures. They're not right angles. Again, no right angles. So rectangle is a parallelogram with 4 right angles. Now let's look at a rhombus. What is a rhombus? Well, it is a parallelogram, so it's in that parallelogram family. It's also a quadrilateral with 4 congruent sides. Congruent just means that they're equal. Let's look at an example. So an example of a rhombus could look like this, just as long as all the sides are the same. And that's really not the best drawing there, so let me try that again. Kind of looks like that kite, but all the sides are the same. There's a square. All the sides are the same. It is a parallelogram. It does have 4 congruent sides. And that non-example would be something like this. A rectangle would not be a rhombus. A parallelogram as such would also not be a rhombus because it doesn't have the 4 congruent sides. So if we go back to part B says, I am a shape that is a parallelogram, a rectangle, and at the same time a rhombus. So I did mention it in each of the drawings. This is a square, and a square does have, think about it, the square does have a shape. It is a quadrilateral. The square has the square has 2 sets of parallel sides. A square is a parallelogram that has 4 right angles. So it's also a rectangle. And a square can be a rhombus because remember, a square is going to have 4 congruent sides. So when you think about maybe a Venn diagram to kind of give you a visual of what this looks like, let's put parallelogram in the middle here. And then, so this entire rectangle is what we say the parallelogram family. But then within the parallelogram, we have a rectangle. But within the rectangle family, we have a rhombus. And within the rhombus, we have the square. So the square, get the idea that that square is inside the rhombus category, it is inside the rectangle category, and it is inside the parallelogram. And we could further that just a little bit and draw this and call this quadrilateral. So those would all fit in the idea of a quadrilateral as well. So let's look at task number 4, and it highlights the standard 4.G.3. So you're recognizing lines of symmetry of a two-dimensional figure, and remember that line is a line across the figure so that it can be folded along that line into matching parts. So we want to be able to identify the line symmetric figures and then be able to draw those as well. And the purpose of this task is for students to, like I said, along with the standard, the purpose is for the students to identify figures that have lines of symmetry, be able to draw them appropriately. And it may be that students haven't learned or have heard about lines of symmetry. So once they start working with this, it would be good for them to think about creating their own shapes that have symmetry and do not have symmetry. Just like earlier, we drew examples of parallelograms and examples of non-parallelograms. This would be a good time for students to think about what does a shape look like that has symmetry or has a line of symmetry and doesn't have a line of symmetry. So to be able to draw examples and non-examples. So with part A here, each shape has a line of symmetry. So we want to draw that line of symmetry. So I'm taking, students could take a straight edge ruler or the side, the straight edge side of a protractor as well, and determine what that line of symmetry would be. And it's okay for students to draw and make a mistake on that. You know, I just drew one vertically. So if I come over here and think drawing this one vertically, is that correct? Does that divide it into two equal symmetric parts? No, divides it into two parts, but they're not the same size. And so that would not be the correct line of symmetry. But if I draw it horizontally, now I've created symmetry horizontally, where if you think about it, can I fold it over that line? Same with the triangle. If I go through the very top vertex and draw it vertically, I will divide that triangle into two equal parts. Notice here, if you think about your vertices, if I draw it this way, it doesn't create the two equal parts. So I have to look at a different vertice. And so here, if I draw it through the right angle area right there, that creates the symmetry. And in this case, I can draw it this way. Line of symmetry will go through that point. There's only one little end point here for that shape, so it would have to go through that top corner. I couldn't draw it this way because this left side, bottom side is not going to fold up on the top side, so that can't be the correct line of symmetry. So it would have to go through this area right there. And then for this shape that's missing a sector, it would have to go through that area or that piece to show symmetry. All right, part B says not every shape has a line of symmetry. Which of the four shapes below have a line of symmetry, and draw that line of symmetry? Well, looking at the green shape, you can pause and try your own through your notes and see which ones would have symmetry, and I'll give you a moment to do that. With the green shape, that would be your line of symmetry. There would not be a line of symmetry with the blue shape, because remember, you're trying to subdivide this into where you can fold it. And the third shape here, your line of symmetry would go through that piece, and it would be able to fold on top of one another. And then finally, this last one would not have a line of symmetry as well. Think about where those pieces, like 1, 2, 3, and 4, think about where one would land if you folded it vertically or horizontally. So first one and third one would have a line of symmetry that you could draw. And then finally, some shapes have multiple lines of symmetry. So when you take this shape here, you would actually have 4 lines of symmetry. And I would ask you to go ahead, if you see the 4, to go ahead and pause the video and complete that in your notes. The 4 lines of symmetry, there's 1. So you see 2 diagonal. Two diagonal lines of symmetry. You'd see 1 horizontal line of symmetry and 1 vertical line of symmetry. And that concludes task number 4. So let's look at task 5. And again, it's asking for you to find all the lines of symmetry. So there could be multiple lines of symmetry here. And then write the number. So in this case, we've got 1 line of symmetry there. Here I have 4-sided shape. So I'm definitely going to have 1, 2 lines of symmetry, but then I also have 3 and 4. So I actually have 4 lines of symmetry with the square. Part C, I cannot find, you can try this, that's not going to work. It's not going to work vertically, horizontally, or another diagonal. So this one would have 0, as well as the lightning bolt. You're not going to find a place that's going to create symmetry with the lightning bolt. And so part D, think about part B and how many sides it has. It had 4 sides. Well, this one has 6 sides. So here's 1 line, 2 lines, 3 lines, 4, 5, and 6. So this has 6 lines of symmetry. And then part E, we've looked at one already like this a few slides ago, and so that line of symmetry is going to cut through at that opening of that missing sector. And so that would be 1 line of symmetry. Here we know that we've got half of the shape. So the line of symmetry is given. Now what does the other half look like? So that's what you're kind of thinking through when you're looking at these problems. So we see the dotted line. So the way I'm looking at this is I've got 1, 2, 3 points to the right of that dotted line. So what if I go 1, 2, 3 points to the left? That gives me a vertex that I can connect. and then connect down, and then we'll see, well, there's the other half that creates the kite, the other quadrilateral. Again, same idea. From the dotted line, I see 1, 2, 3. Down here, I see 1, 2, 3. So I'm just going to go 1, 2, 3 to the right, 1, 2, 3 to the right. Use my straight edge tool. Create that. And there is my other half. And I should see a shape that's cut into 2 equal pieces. So that concludes task 5. So let's look at task 6. And notice this is one that combines multiple standards. So we're thinking about looking at the lines, the line segments, rays, angles, two-dimensional shapes. So they parallel, perpendicular. We're looking at symmetry. We're looking at all of these things. But in this case, you have, let's say, A, B, and C, and you're just trying to determine the characteristics to help classify. So when we look at part A, we're thinking about, all right, how can we give it a heading that makes sense? Thinking about acute, right, obtuse, scalene, isosceles, and equilateral. All right, well, just by scanning them, we see that we have triangles. And just the observation looks as if this one's equilateral. It looks as if this one is isosceles, this one's isosceles, and 4 and 5 don't quite fit. They don't look like an equilateral, and they don't look like an isosceles. So we can't use scalene, isosceles, or equilateral, one of those, to identify all of them. So we've got to look elsewhere. So what about acute, right, obtuse? Well, none of these have obtuse angles. None of them have right angles. So acute angles will have to be the best term to classify all the shared attributes. Well, let's look at B. Again, look at everything, we see triangles. But when I look here, I think on triangle 1, those two sides look pretty much the same just by viewing it. On triangle 2, those look the same. Triangle 3, those look the same. Triangle 4, I do see a 90-degree angle. The rest of them do not have a 90 degree, so number 4 is a little different, but these sides appear to be equivalent. And then on number 5, those sides. So again, to think acute, right, obtuse, scaling, isosceles, or equilateral, well, some of them have obtuse angles, like triangle 1, triangle 2. Some of them have acute angles, like triangle 3 and triangle 5. And one has a right angle, which is triangle 4. So we can't specify it by angle. But we can specify it by the type, thinking about side length. And so this would be your isosceles. And then finally, part C. Look at the attributes here. I see all triangles. I see a right angle here with number 1. I see a right angle with 2, a right angle with 3, right angle with 4, and a right angle with 5. Now, this one may appear to be isosceles, and this one may appear to be isosceles right, but number 4 doesn't look that way. Number 5 doesn't look that way, as well as number 1. So we can't really specify it by the side length. We can't say it's a scalene right, because they're not all scalene. Some of them appear to be isosceles. So we would have to look in this one and say that right angles are the common attribute amongst all of them. Now, if we take some different shapes here, and I want you to draw lines to identify each triangle according to the type and the side length. So the angle type and the side length. So let's look at A. A does have a right angle, so it would definitely, right would go with it. But this side length is smaller than this one, which this one is smaller than this one. So scaling right would have to be part A. And then part B, it appears that these segments are the same, and we have an obtuse angle. So it looks like obtuse and isosceles would identify that. And then with part C, it looks as if it appears that all sides are equivalent. So that would lead to equilateral, and all of the angles are acute. So this would have an acute angle, 3 of them, and it would be an equilateral. And then finally, the last part of this task is to identify any symmetry lines. And with A, with being the different side lengths, I cannot do that. So there's not a line of symmetry there. There is a line of symmetry on part B, and then part C, there would be a line of symmetry here, here, and here. So this would have 0 lines of symmetry, 1 line of symmetry, and this one would have 3 lines of symmetry. So that's going to conclude part 1 of this video series on 4th grade geometry. And we will resume with part 2